in a second. So HPLC is this system here that we're looking at. It involves, here is your substance to be tested. Yeah, and it's dissolved in a solvent. Now what happens is you pump that through and you have this injector auto sampler. Oh, sorry, here's your solvent. Sorry, that's not your sample. So your solvent is kind of pumped through the whole system, is this blue bit here. Yeah, so solvent is just, its job is to carry the sample. So it's just going to pass all the way through. So the solvent is going to pass all the way through, up, pump all the way through the column. This is your stationary phase in the HPLC, all the way through the detector and down into the waste. What we do here is, this is where we put in our sample. So our sample would be our compound that we want to separate. We're going to inject it into this moving solvent. It's going to pass along through here. It's going to separate in the HPLC column. And they're going to time how long it takes to pass through the detector. So some things will move fast and they'll go through the detector first. Other things will move a bit slower, so they'll go through the detector a little bit later. So reading our notes, it says HPLC is a specific type of what we call column chromatography, because there's a column in the middle called HPLC column, and we can use it for qualitative and quantitative analysis. HPLC is more sensitive than general column chromatography and is used routinely in industrial and pharmaceutical applications. So we use this a lot. So the stationary phase in this case is actually a solid, yeah, it's like a solid kind of mesh almost, and it's thin. It's not mesh, it's just this solid, and it's thinly coated in a very viscous medium. So what is viscose? Viscous is something that is kind of thick and sticky like honey. So imagine it's like a bit of plastic, for example, covered in honey. That's what the inside of your column looks like, but it isn't a piece of plastic covered in honey. Now the mobile phase here, this is the mobile phase. The mobile phase is your solvent, and it varies dependent on what you are trying to separate. So usually the stationary phase, that column, it stays the same kind of materials, but the solvent will be different depending on what you're trying to separate. So the mobile phase travels, and the word that we use for this, for travels, is elutes. So that's in the brackets there, elutes. So the mobile phase travels or elutes through the entire column, sweeping the components along. As they move through the column, through the HPLC column in the middle here, as the substances move through this, they kind of slow down depending on how much they adsorb to the stationary phase and what rate they desorb. So some of them won't have a very strong rate of adsorption, so they'll pass through very quickly. Some of them will have very strong adsorption, so they kind of pass through a lot slower. And it's that separation that we're looking for. So as they move through the column, the components will adsorb onto the stationary phase and desorb off again to varying degrees, thus creating the separation of the components. So what are some of the special features of HPLC versus, say, normal column chromatography? This one's quite expensive. So why do we want to use the expensive machine? So the solid particles of the stationary phase are about 10 to 20 times smaller than a usual column. So essentially it gives you a lot more places for adsorption to happen. So that gives you an increased accuracy. So more surface area because of that increased number of particles, because they're smaller. So more surface area increases the amount of adsorption and desorption, which means improved separation. So it gives more resistance because it's got an increased surface area. So you're going to get more resistance of the mobile phase. So we need actually high pressure. So for high performance liquid chromatography, sometimes you can call it high pressure liquid chromatography. So you're actually pumping. So this pump here is going to provide pressure to pump those molecules through the HPLC column. So the range of different stationary phases, so you can change what your column is made of. So you can just kind of take it out, switch it out, put in a new column. Can be used to improve separation. So depending on what you're trying to separate. And the mobile phase is chosen for its polarity to assist separation. So it's really important that we choose the correct mobile phase and the correct stationary phase. If you get it wrong, you just wasted your sample. You're going to have to go back again. So we actually use a guide essentially that tells us the best kind of mobile phase and stationary phase to use for different types of compounds. And it's all got to do with the polarity. So the column is only 20 centimeters long. So it's only probably about as long as that pencil there. And it's made of stainless steel. So it's not made of plastic, it's made of stainless steel. And it can separate quite big components, things that have an MR of 300, of greater than 300, which is pretty good. And it can also detect compounds that decompose on heating. So you can detect things that normally, if you were to heat them up in a different type of machine, they might decompose. So you can use this cold and just use pressure to push them through the system. So what we can do is we can do what we call a qualitative analysis. Now I haven't got the qualitative analysis on here, but qualitative analysis is where we actually use, and sorry guys. So here is your stationary phase. Here is your column, and we detect different things that pass through. So we run it for a certain amount of time and say you detect that they came through in this order. So the one at the top has moved the fastest. So what we can do is we can actually measure. So here is the line of origin. We can actually measure, and here is I'm doing it on paper chromatography because it's easier to visualize. So here is the solvent front. Sorry, solvent front. And so what we can do is we can measure as a percentage the distance a particular substance has traveled. So RF is going to equal to distance traveled by the substance over by substance. So that might be substance 1, 2, 3, or 4 over the distance the solvent front. So how far did the liquid travel? And what it gives you is it gives you a decimal. So it's always less than 1, and it'll give you a decimal. And that will give you kind of a value for a particular substance. Now, if you use the same mobile phase and same stationary phase, you should get the same RF value for a particular substance. So RF values can tell you what the substance actually is. So that's the qualitative analysis of chromatography. Now, the quantitative analysis has got to do with HPLC more specifically. So as we said, it's got to pass through this detector at the end here. So essentially they time, where's my little stopwatch? Here's my little stopwatch. They time how long it takes for each substance to pass through that detector. And so that gets measured on my x-axis here, that time. Now, as each substance passes through the detector, they can also measure how intense it is, how high that peak is. So when you measure how high that peak is, you can see here, this peak here is the highest, and it passed through after about 4 minutes. So I would say that there is more of this. There are how many substances? There's 1, 2, 3 substances, because there are 3 peaks. And I would say that the area underneath this peak, this area, is going to be able, there's an equation you can use, which will give me my quantity of the particular substance. So the area under the peak gives the relative amount of each component of the substance. And what we can use is we can use a set of standard components. So we know, again, just like before with the UV vis, you can use known amounts of a substance and you can create what we call a calibration curve for a particular substance. And then we can use that. So we know how much is in there and we measure the area and we plot that out on a curve like this. Okay, so here are our known concentrations. Here are all the little curves. You can see how there's like different curves hidden in here. And you plot them out on a curve like this. And what it means is we can actually use that peak area. Say I find an unknown one here and it's got a peak area of 1500. I read across, I read down and I go, okay, if it's got a peak area of 1500, then I know that my concentration is going to be about 63 milligrams per mil. So you can use these calibration curves in a very similar way to use that, but they have to be comparing standards at the exact same peak, because what we've said before is the number of peaks equal the number of components. So the area is going to equal the amount or the quantity of each component, but the number of peaks is going to give us how many components there are. So what are some applications? Some applications of this. We can use this to analyze proteins, peptides. We can use it to analyze how much cyanide there is. And I know that seems weird, but cyanide analysis, cyanide is used for gold extraction. So you want to make sure you don't have too much contamination at the end. We can use it for flavonoid analysis, which are exactly what they sound like, molecules that create flavors in fruit juices. You can use it to analyze how many toxins there are in particular types of shellfish, like mercury. You don't want to eat shellfish that has too high a concentration of mercury. Pharmaceutical analysis, making sure a drug is exactly what it says it is on the label. If it's not, then they can be taken off the shelf, for example. You can also analyze caffeine content in drinks. You could also use gas chromatography for this. Also the proportion of different food molecules in a particular food product. But essentially chromatography has a bunch of different applications to it. But it's a really interesting way of, again, figuring out concentrations of unknown substances based on known quantities. And that's it.